All right. Welcome, ladies and gentlemen, to this afternoon lecture, my fourth lecture in the series on computational representation theory. And today I want to tell you what condensation is. This is an enhancement to the METEX. I have talked about the METEX yesterday, and I will give you an example, at least some ideas of how condensation was used to compute the two modular character tables of the Fischer group FI23. Again, G is a finite group and F a field. And A is a finite dimensional F algebra. For example, the group algebra Fg. J of A denotes the Jacobson radical of A. I think we are going to make use of this. This is the intersection of the maximal right ideals of A. We will make use of this in particular, I think, in the lecture tomorrow. The intersection of the maximal right ideals of A. And well, representation theory of A is the study of A modules. So by mod A, I mean the category of finite dimensional right A modules. So the objects are A modules, or equivalently you may view them as A representations. And the morphisms are A module homomorphisms, or intertwining maps between the representations, if you like to think in this picture of representations rather than modules. Well, the METEX maybe nowadays, if you just naively start it, will be able maybe not the gap METEX, but if you use Ringer's METEX, which is a C standalone version, will be able maybe to deal with modules of degree up to 200,000. You remember the METEX, what does the METEX do? So it has matrices, A1, just for the simplicity, let me think of two matrices in FD cross D, and if D is large, and this is of course the applications we have in mind, it has to compute elements, words in these matrices. For example, A1 times A2 plus A1 plus A2, or even more complicated words. So it has to multiply matrices of this size. It also has, so this is, if this is the matrix B, and if it has a small co-rank, then it has to find the null space of B. So it has to do Gaussian elimination on this matrix. And all these operations, these matrix operation, multiplication and Gaussian elimination, are essentially D cubed operations. So it goes with a cube of D. So if D increases by 2, then the work we have to do increases by a factor of 8, essentially. So you see, these are the bottlenecks. And then it has to do the spinning algorithm, you see. If you have a vector in a null space, it has to apply VA1, VA2, and so on to elements, but then it has to check linearly independence of vectors of this size. And again, this is done doing equalization, of course. So Gaussian elimination again. Okay, so all these are quite time-consuming. This is the reason for this restriction, and of course also the size. A matrix of this size is about 5 gigabytes on a computer. So if you want to fit one matrix into or two matrices into your CPU. This has to be large. Yeah, and at the time when the METEX was done, CPUs were not large. So we could only do small matrices. But this is increasing, but nevertheless, this, I mean, there is a limit, and maybe this is about 200,000 if you do it naively. And of course, if you work over F3, things get worse. And if you work over F5, or if you have to use an extension field of F3 of degree 2, things get even worse. And this is why I think Parker and Thackeray came up with the idea of condensation. So there should be a way of condensing these large matrices in a certain sense, such that you can still apply the METEX to the condensed matrices and get back the same information you want. And I mean, recently I have heard a talk when someone was talking about condensation, and essentially this guy told the audience, and there is some truth in this, condensation just means that instead of a big matrix, you look at some upper left square corner of the matrix. Well, it's not exactly like this, but this is the idea. Okay, so yeah, we work with idempotents. So we want an idempotent, just an element in the algebra which squares to itself and which is not zero. And then we get a functor from the module category into the category of modules of another algebra, namely EAE. It is easy to see that EAE is an F algebra in its own right with unit element E. And if you have a module V, it is sent to VE. And maps are just restriction of maps. Maps between modules are just restriction of maps. So this is an exact functor. So it sends short exact sequences to short exact sequences of modules. And also it is easy to see if you have a simple module. So if S is simple or irreducible, which I'm using this synonymously, then two things can happen. SE is simple or zero. It can condense to zero, so this map is called condensation with an idempotent. And so in particular, if you take a set of simple A modules, remember these are the irreducible representations we are looking for if A is the group algebra. And then maybe some of them, the first M of them, do not condense to zero and the rest of them condenses to zero. Then this is the second fact. These are exactly the simple modules of this algebra EAE. So every simple module of EAE is a condensed simple module. Yeah? And in particular, as the condensation functor is exact, it sends a composition series of a module of A to a composition series of VE. You see, some of the composition factors, they just disappear, but you still get a composition series. Some of the composition factors, they just might disappear, but you still get a composition series. And you see, I mean, reducing a matrix representation which is not irreducible amounts to finding a composition series on the module it acts. Okay? Okay, so in a good world, of course, this M is equal to, what was it here, N. So none of the simple modules would condense to zero. And then we would get, get the same set of simple modules and we would find the same internal structure of a module and its condensed module. But of course, the point is, depending on the idempotent E. Of course, you can take E equal to 1, then nothing interesting happens, then the module stays as it was. But if E is not 1, usually this VE has a much smaller dimension. It's a subvector space of V, after all, and usually has a much smaller dimension. And you see, of course, this was implicit in the metex I told you yesterday. The metex finds composition series of modules. It finds invariant factors, and then it can find the projection onto the quotient module and on the submodule, the restriction to the submodule, and then it iterates this process. So the metex finds composition series of modules. So instead of applying the metex to this situation, where we have a group algebra, we apply it to this situation where we have a condensed group algebra. And this is in general, of course, not a group algebra anymore. One of the reasons why I told you, why I introduced the metex yesterday for arbitrary finite dimensional algebras rather than group algebras. Okay, so in fact, we get a MORITA equivalence. Okay, let me tell you about a MORITA equivalence. So if none of the simple modules condenses to 0 with this idempotent, so if SE is not a 0 module, then condensation, so this map, this is condensation with E. This map, yeah, this map is a MORITA equivalence. Well, what is MORITA equivalence? A MORITA equivalence is an equivalence between module categories, which essentially tells you that the two categories are equivalent, which essentially tells you that the two algebras have the same representation theory. So you can map the simple modules to the simple modules, and any module to another module which has the same composition series, okay, which have matching composition series. Yeah? So this is my notation for the right regular A module. So A viewed as a module over itself. If you decompose it into indecomposable direct summands, these are the PIMs, the principal indecomposable modules. In my lecture 2, we had PIMs occurring in the theory of Brauer characters. So these were characters which arise from looking at columns of the decomposition matrix and reading this column as a linear combination of ordinary characters. So a PIM in this sense is indeed a projective indecomposable module, or arises from a projective indecomposable module of the group algebra. But I mean, I don't want to explain the details, but there is a projective indecomposable module of FG, which can be lifted to a projective indecomposable module over a suitable valuation ring of characteristic 0. This has an ordinary character, and the ordinary character of this lift is the PIM in the sense of lecture 2. Okay. Anyway, there's a connection between the two notions. Projective A module is a projective module is a direct summand of a direct sum of A modules, but this is the same as a direct sum of PIMs because of the Hull-Schmidt theorem. Every module decomposes uniquely into a direct sum of indecomposables. And, well, a finite dimensional F algebra B is MORITA equivalent to A if B is isomorphic to the endomorphism algebra of a module Q of A, where Q is projective and contains every PIM of A up to isomorphism at least once. Okay? So you take every indecomposable direct summand of A. Well, if you look at the endomorphism algebra of A itself, this is A. But if you look at a submodule which consists of a direct sum of PIMs, each PIM, each isomorphism type occurring at least once, The endomorphism algebra will be of smaller dimension, but this is the algebra MORITA equivalent to A, and this is MORITA equivalence. And as I said, MORITA equivalent algebras have the same representations in the sense that their module categories are equivalent. And this is exactly what we want. So we, at least, okay, of course, in the first place, we want the dimensions of the irreducible representations of a group algebra. If we do MORITA equivalence, we get sort of images in a MORITA equivalent algebra of the irreducible representations, but they don't necessarily have the same dimension. So we lose the dimension. But we have more information on group algebras, which allows us to recover the original dimension from composition theories. Anyway, so, okay. Sorry? Projective indecomposable or principal indecomposable module. So you write A. So it's the right ideal. And indecomposable, which means that you cannot write it as a direct sum of two smaller modules. These are the principal indecomposable modules, and these are projective in the sense of homological algebra. And every projective in the sense of homological algebra is a sum of these. Okay? This is because the algebra is finite dimensional, very nice situation. Of course, we want to make this theoretical background. Yeah, it's a nice theory, but can we make this work on a computer? We need idempotents. So we need idempotents in the group algebra. There's always one idempotent. Well, the trivial element, okay? This is an idempotent. Yeah? This doesn't work. But if you have an involution, say, an element of order 2, and the field is of odd characteristic, you can look at, so the involution maybe is tau, so if you look at 1 plus tau and multiply it with itself, in the group algebra, what you get is 1 plus, plus 2 tau, plus 1. So you get 2 times 1 plus tau. Okay, so if the characteristic is 0, you get 0. But if the characteristic is not 0, you get an idempotent by taking 1/2 of 1 plus tau. Okay, so this is quite nice to begin with, but not good enough because I mean it's too small in a sense. But of course, this can be generalized. Take in the group algebra the sum of all elements of a subgroup, which has to be chosen such that the characteristic does not divide the order of the subgroup, and then take this thrice idempotent. So this is the idempotent of our choice. We have to look for subgroups, and then which are not divisible by the characteristic of the field F we look at. But of course, there are other obvious idempotents which can be used. You see, it is one thing to write down an idempotent, but then on the other hand, we have to make use of it in the sense that we have to be able to compute the action of certain elements of the condensed algebra, of this condensed algebra on certain elements of this module, on this module. So this makes it not so clear which idempotents to choose. For example, you can take an idempotent which corresponds to a linear, to a one-dimensional representation of the subgroup H. So you would take this as an idempotent. This is also quite nice and can be used. So these are the idempotents we use in condensation. Okay, now the next step is, once we know which idempotents to use, okay, we want to apply the metex to this this module. For this, we need the action of the algebra on the module, given in terms of generators of the algebra, written as matrices describing the action, okay? So we have to compute the action. This cannot be done for general modules, but for certain modules, we can do this. You see, we want to take modules for the group algebra, representations for the group algebra, and we want to apply condensation to modules which have a huge dimension. Of course, we cannot make the module first and then condense. This is exactly the point. We have to be able to compute the condensed action before making the module. And of course, in certain situations, the module is given in a different way. For example, if you have a permutation module, then in fact the module is given, the module for the group algebra is given as a permutation representation. So this is a much smaller data set. You have 2 permutations for the group, which you don't even want to write down. I will tell you in a second how you may think of it. So the permutation modules. So this is the module over F, which has a basis which is permuted exactly as G permutes the set omega. Then it is more or less clear that the condensed module with respect to this idempotent consists of the H fixed points in V, just the H fixed points. Okay. And now, well, which elements to choose in this algebra EAE? We could take any element in A and apply and try to find the action of EAE, but we take group elements. So given a group element G, we have to determine the action of this element in the condensed algebra on the condensed module, without the explicit computation of the action of G on V, without writing down the permutation matrices, even without writing down the whole permutation, because we have very large permutations. You see, the permutation representation might be given in a different way. You might be able to say, well, let's look at another representation. Let's look at a linear representation, W. So in mod FG. Yeah, and let's choose a non-zero vector in W. And let's look at omega, just the orbit of W under G. Sorry. This is a beautiful permutation representation which you can just specify on a module which you can write down and a vector. So in a sense, you delinearize again. You make from linear representations, you make permutation representations by letting the group act on the individual vectors. And of course, these are huge orbits, or you don't want, maybe sometimes you don't even take vectors, we take subspaces of dimension 2 or of dimension 4 and let the group act on it. So these orbits are huge. But this can be done. So this was already done. I think this was the beginning of condensation back in the 1980 or 81. I think Parker had the ideas, and Thackeray wrote them down in proper mathematical language and implemented the method. And the first modules they applied this condensation was permutation modules. So how can this be done? Well, so you have a permutation representation of the group on a set omega, specified maybe in this way. And you have a subgroup. The group G is given by a generating set. In this maybe has 2 matrices in the action of W. So W is much smaller than the V we want to condense. H is given in terms of the generators in terms of words in the generators. You look up Rob Wilson's database and find the subgroups H you want to, or you make them in a sense. Usually they are not in Rob Wilson's database because H is not in general a maximal subgroup. We cannot be in general a maximal subgroup because of this restriction that P, the characteristic of F, should not divide the order of H. So let's suppose we can compute the H orbits on omega. Then the orbit sums inside this vector space are basis for the H fixed points. And with respect to this basis, we want to make a matrix, Aij, of the action of EGE on this set of H fixed points. And you see, this is just, I mean, this is, you can work out yourself. This is the formula. You take the number of elements in omega j, which are translates by G from the set omega I, and then you have to normalize it. Yeah, so this is what you have to compute. So this is what you have to compute, this number. For each element in omega I, you apply to each element in omega I, you apply G, and then for each other orbit, you see, I mean, when does it fall into this orbit, and you count. So this is, Richard Parker explained this to me. I mean, he did not really explain it in these mathematical terms. Yeah? He said, you see, you apply G to an orbit, and every time you meet another orbit, you drop a number. This is how he explained it to me, but this is what we made of it. Yeah, see? Yeah. You apply G to an orbit, and every time you meet another orbit, you drop a number. Yeah, this is counting. But anyway, this is the formula. So in order to perform these computations, we need to be able to compute somehow these orbits and their length, and decide for any element in omega in which orbit, to which orbit it belongs to. But usually we are not able to write down the whole orbit, you see, because it's too large, too long. But anyway, this can be done. You see, in actual computations, we had orbits of length 10 to the 15. So the elements of omega cannot be stored in memory. Well, again, Parker and Wilson suggested what they call direct condensation methods, and these ideas were later expanded by many people, among others Frank Lübeck, Jürgen Müller, Max Neunhofer, and Gene Kuberman. And the principal idea is the same as in Heiko's talk, isn't it? I mean, instead of enumerating the H orbits, we look at suitable subgroups and first enumerate the orbits for the subgroups. And then it's quite sophisticated. And if this doesn't work, you iterate this idea. You look at subgroups of the subgroups. Yeah? And then somehow you don't store the orbits, but what you do is, so you don't store the whole orbit, but what you do is you store a couple of points of this orbit. For each orbit, you store a couple of points and an algorithm which will guarantee that given any element in omega, if you apply it, it will send you to one of the stored points. Yeah? So this can be done. You store a couple of points for each orbit, and you have an algorithm which, given any point, brings you back. So like a researcher who would be sent into some desert, you see, and there are some flags, but he has a way of finding back to one of these flags which are spread over the desert. This is what they do. And of course, the details, again, depend on the realization of the action on omega. I mean, for example, it might be the case that you have, you say, okay, I want the permutation action of the baby monster on a maximal subgroup, yeah? On the cosets of a maximal subgroup. Or I want the permutation action of the group on the vector spaces of dimension 4 in a given module, and so on and so forth. So I cannot tell you more details because it depends on the realization of this action. So this is one of the ways one can condense. The next is where a module can be given with smaller pieces is if you have a tensor product of modules. You have two small pieces, but together the tensor product is too large. So if you have two modules and you want to find the action of EGE on this tensor product times E on the condensed tensor product without, of course, explicitly computing the action of G on V tensor V, on V tensor W first. And this can also be done. I omit the details, but it can be done. And also for induced modules, if you have a module W of a subgroup M of G, then you can define the induced modules. In terms of modules, it's just this tensor product. So its character is the induced character I introduced in the first two lectures. You can do this. And again, given this module, which is maybe manageable, and a group element G, and the subgroup M, find the action of EGE on this condensed induced module without, of course, computing the induced module first. And again, this can be done. So this is an algorithm to Müller and Rosenbaum. So this, all this goes back to 1997. But in effect, all these three examples of condensation, namely condensing a permutation module, condensing a tensor product, or condensing an induced module, are sort of different images of the same thing, namely condensing homomorphism spaces. So if you have a subgroup again, a subgroup of G and W and Fm module, and V a module which has a right Fm action and a left Fg action, and these actions commute, you can make this homomorphism space into a right Fg module by just applying this rule. So phi is one of these homomorphisms. Phi of G would be the homomorphism which you obtained by acting with G. You apply it to a vector V, and this is the rule. I mean, this is standard construction in module theory. And then you see, it's easy to see that if you apply this to the subgroup M, and the module W is just a trivial module, and V is the trivial module, no, W is the trivial, and V is the group algebra, you get the permutation module corresponding to the action of G on the right cosets of M. Or if you take the dual of V, the dual module, and W an Fm module, again an Fg module, and for M you take the trivial submodule, you get the tensor product. Or you take the subgroup M and you take Fg and W, then you get the induced module. So you have to be able to condense this homomorphism space, which gives you three examples. And this was then developed by Lux, Neunhofer, and Nöske, developed general condensation methods for all these homomorphism spaces. So in a sense, it unifies the things we can do. Well, some applications. I think the first application was the proof of the existence of J4, where they really produced this 112-dimensional representation over the field with two elements, which gave J4. I think this was the reason why condensation was invented. Thackeray, in his PhD thesis, used it to compute the two-modular character table of the McLaughlin group, and at the same time answering a question of Brauer to the negative. So it gave an example which And then later, when I entered this game, Lux and Müller and Kuperman, we computed the Brauer tree of the Thomson module of the Thomson group, modulo 19. So this was already a very large example. So we had to condense a permutation module of this degree, so 1 billion essentially. The condensed module has only dimension 1403. This was manageable at that time. But we had the field with 19 elements. Okay? So the main work was to make these condensed matrices. Then other guys determined with similar methods some ambiguities which were left over in the Brauer trees for the Lions group, modulo 37 and 67, where they had to condense a module of about the same, slightly larger. And I will tell you about more applications later. Okay? Well, this is a further application actually. What is the basic algebra of an algebra? I have already told you. You may take all the projective indecomposable modules. And if every module occurs only once in its isomorphism type, the algebra is called basic. So if all these PIs over there are not isomorphic, it's a basic algebra, or alternatively, the modulo its radical, it's a direct sum of division algebras. And how do you make out of any algebra a basic algebra? You take all the PIMs only once, take their direct sum, take its endomorphism algebra. So this is MORITA equivalent to A, and it is a basic algebra. It is a basic algebra, MORITA equivalent to the original algebra. And it has much smaller dimension usually. And this is in a sense the smallest algebra by dimension, MORITA equivalent to A. And this is an application which is pursued by Klaus Lux. So he does a lot of work in this direction. If the dimension of A is very large, it may be too difficult to find its basic algebra explicitly. One will do with any algebra which is MORITA equivalent to the original algebra, but which has a dimension which is manageable. And this is what Klaus Lux does. He constructs algebras of feasible dimensions which are MORITA equivalent to group algebras, or rather to blocks of group algebras. So we can also decompose the group algebra into indecomposable two-sided ideals. The blocks, these are algebras in their own right. So we need idempotents. We need an idempotent such that no simple module condenses to zero. And this is something that can be checked. You see, if you have a subgroup whose characteristic does not divide H, and you still take E to be the trace idempotent, and you have the Brauer character of a simple module S, it suffices to restrict this Brauer character to the subgroup H, compute the scalar product with a trivial character. Scalar product, the inner product in the usual sense of ordinary characters, because H is not divisible by the characteristic. And if this is non-zero, then this condensation is non-zero. After all, what it tells, I mean, the fact that this is non-zero says that H has fixed points on this module, and says the trivial character appears as a submodule. Okay. So for example, the principal block of the Hickman-Sims group modulo 5, he takes a group of order 192. This is the dimension of the principal block, 15 million, but the condensed algebra has only dimension 767, so this is feasible. And of course, applications. So this is on the homepage of Klaus Lux. And applications, you can compute Cartan matrices for group algebras, cohomology computations, because cohomology, of course, is independent of the MORITA equivalence class of the algebra. Okay. This is a picture out of the history of mathematics. This is how I was taught the condensation for the first time. On the back of this piece of paper, you can imagine what it is and where it was. I think it was in Café Kittel in Aachen. So this is how Richard Parker tried to explain to me his new multiplication on the double coset algebra. But it took some time to make sense out of this until we had this formulation which I have presented to you. But anyway, so this is just Okay, so far so good. But now comes the biggest problem with condensation. Sorry? No, the field is characteristic. Well, of course it would also work, yes. Yeah, it would also work. Yeah. Of course, if you have an idempotent, if you find an idempotent. Yeah. No. If you take a central idempotent, you will not gain much. I mean, you will just project to the homogeneous components. Yeah. Yeah, of course, if you have a suitable idempotent, yeah, of course, you can do the same, yes, of course. This theory, I mean, the first part of the theory was not really restricted to characteristic. I mean, there's no restriction. It works for any field, for any algebra. But of course, if we want to apply it for fields of characteristic P. So when we investigate a module, this module VE through the metex, we use matrices of generators of E. Yeah. So how can we generate this algebra? So this is the main problem. How can we be sure that our condensed matrices we compute generate this algebra in its action on the condensed module? In general, it is not the case that if you take a generating set for the algebra and you condense the generators of the generating set, that you will get a generating set for the condensed algebra. This is bad luck. This is one of the problems we face. So we take a subset of, we take a generating set of the algebra and we condense the modules. So in principle, we only work with the subalgebra of the condensation algebra, only with a subalgebra with C. So we work with a couple of matrices of this form EGE, where G is a subset, where G runs through certain elements of the group. And then we work with this algebra, which is generated by these condensed matrices, but in general, we don't know whether it's the whole algebra. So we work with some subalgebra C of it. Yeah? We can draw conclusions on V from VE with the action of this, but not from the restriction of VE to Z. So somehow we have to make sure that on this restriction nothing bad happens. And this is one of what I meant when in my second talk on the modular atlas project, when I told you that some modular character tables are known up to condensation. It's exactly that problem that has to be solved, this generation problem for these condensed algebra. So the people who have computed, they are quite sure that they have enough generators, maybe not to generate the algebra, but that the algebra and this subalgebra have the same number of simple modules and the restriction preserves the equivalence or isomorphism, but they have no proof. And so up to this proof, they have found all the modular character tables, so up to condensation. But there is a special situation where this can be done. So this was done by Felix Nöske in his PhD thesis. Suppose your condensation subgroup H has a large normalizer. is normal in some n, and n may be a maximal subgroup. So this happens if you want to condense in the monster modulo an odd prime. You take a maximal subgroup, 2 to the 1 plus 24, we learned in this lecture, times Conway 1. And then you have, you take as h, this 2 to the 1 plus 24, and that's n. And then you only need, what you need is a set of double coset representatives for this maximal subgroup, usually that are not so many. In the monster that are many. You cannot do it in the monster, but in the Fischer group, it was about 300. Yeah? And then you only need a generating set for the group n, or actually only for n modulo h lifted back to n. And as I told you, every sensible group is generated by 2 elements. You need 2 extra generators. Yeah? And if you take such elements, so representatives of a double coset, of double cosets, and these can be computed with gap in another representation of the group you can compute with, and generators for this group n. Then, in fact, the condensed elements generate the condensation algebra. And then there are some more sophisticated methods, but we haven't found application. Another problem, Felix Nöske solved this. The other idea you could have, if you take a larger subgroup H, but then some of the modules disappear. Some of them condense to 0. Then you take another subgroup, H prime, where maybe you are lucky and these modules which condense to 0 with the first subgroup don't condense to 0 with the second subgroup. Then you have some matching problem, because every condensed module, a simple condensed module, corresponds to an irreducible module for the group algebra, and then you have to match them. And this can also be done. This can be done. So this is another approach. Work with 2 different idempotents. Okay, or you can, another idea, you can condense projective modules. In this case, if you take a projective module, is a special projective module, a direct sum of the group algebra, where E is the projection onto the direct sum. In this case, you can compute the dimension of its endomorphism algebra just by ordinary character theory. You know the dimension of this algebra beforehand, and if you can compute the dimension of a finitely generated algebra, and this is a program by John Carlson, which I'm going to tell you about tomorrow, then you can check whether you have enough generators. You know this dimension beforehand from a character theory calculation, and you can compute the dimension of the condensed algebra, and then you can check. So this is something we want to exploit in the Thomson group, modulo 5. We have already made some progress some time ago, where we condensed the projective module of this dimension, but we need to condense a module of this dimension, and so we have not done this. The Fischer group is such a group of this order, Fischer 23. It has a maximal subgroup of this index. So this is the smallest permutation representation of the Fischer group on a 2 times Fischer 22. And we have computed its 2 modular character table, and in the last 1.5 minutes, I would like to tell you what we have done. F is the field with 2 elements. It turns out that it's a splitting field. We take the permutation representation on this, these many points on 2 times Fischer 22. And then using just the ordinary metex within gap, we found these composition factors. The composition factors are denoted by their degrees. And this, at that time, it took about 4 days of CPU time in 8 GB main memory. Today's it would probably be slightly faster, and in Ringes metex it would even be faster. And then, so we have 5 modules. We can build 10 different tensor products, and we have so the largest one has this dimension, 370 million, and we have condensed all these tensor products. So we cannot store this matrix, it's out of reach. We take a subgroup which is inside a Sylow 3 subgroup, which has about 20,000 order. We found, after all the calculations, that the two algebras are MORITA equivalent. The dimension of the condensed module of this is something which is feasible. But it took about 1 week of CPU time to compute the action of one element on this condensed module. We had 308 of them. Of course, we didn't wait 308 groups. This can be parallelized. We use different computers. Anyway, every irreducible module actually occurs in here, but we need all the other modules to analyze, finally to find these degrees. So the degrees in brown are the ones we didn't have to find because they lie in other blocks and were known. So we were lucky. So the largest irreducible we has this dimension, 34 million, and similarly Fischer 23 has been finished this year, modulo 3. So Fischer 23 has been done, thanks to the work of Klaus Lux, and I thank you for your attention.